moving freely and effortlessly through the air. Since time immemorial, humankind has been fascinated by the flight of birds. With serene poise, the seagull glides over the sea, poetry in motion. But there's more to flying than aesthetic appeal. Birds are genuine athletes. When swooping, a hawk can reach speeds of up to 300 kilometers an hour, and geese in flight ascend to altitudes of up to 8,800 meters. Visionaries, scientists and pioneers of aviation such as Leonardo da Vinci saw flight as one of the greatest challenges facing humanity. For decades they observed bird flight, analyzed its motion and studied the anatomy of birds. They devoted great attention to the form and function of the wing and devised initial models. Otto Lilienthal was the first to build an aircraft that could glide through the air. But he did not succeed in deciphering the flight of birds. The best pilots are to be found in nature, and in engineering terms, the efficiency of birds' flight remains unparalleled even today. Birds are experts in efficient movement through the air. The muscular strength of their wings provides them with both lift and forward propulsion. During flight, their sensory organs help them to constantly measure and optimize their movement. They make the best use of airflow under all conditions. The company Festo, a global player in the world of pneumatic and electrical automation technology, likewise has superior mastery of airflow. The development and production of the latest generation of cylinders and valves relies on making optimum and efficient use of the flow of air in automation technology. As part of the Festo Bionic Learning Network, in which insights from nature are transferred to products in the field of automation technology, a number of filigree ultralight structures developed in accordance with bionic principles have already taken to the air. In air jelly and air ray, for example, helium provides the necessary buoyancy. These were lighter-than-air devices. Designing a bird that's heavier than air, however, proved a difficult challenge even for the experts at Festo. The company's engineers and scientists pooled their resources to achieve something that no aviation pioneer or scientist had attained before them: deciphering the flight of birds. The idea for SmartBird was born. This project is headed by Markus Fischer, who has supervised many programs from the Bionic Learning Network. I find it extremely fascinating in engineering terms to emulate the flight of birds. This is a great challenge. Until now, scientific literature has claimed that it's impossible to construct a bird that flies with articulated wings. We created a team that we believe could succeed in achieving this. And what could be a better role model for SmartBird than the herring gull, with its impressive flight characteristics? On the initiative of Festo, Markus Fischer appointed a development team that included the experienced model makers Rainer and Günther Mograuer, who in the past years had already been involved in many projects of the Bionic Learning Network. Dr. Wolfgang Send, a former employee of the German Aerospace Center and an expert on bird flight, assumed the scientific supervision of this project. The team is completed by the research duo of Agalia and Christoph Jebens, who are responsible for the control electronics and software. One thing was clear right from the start: the new model was not to be built with rigid wings, but would fly like a real bird. There'd been no end of attempts to recreate the flight of birds, but these had never progressed beyond the model of an ornithopter, with rigid wings that kept the model airborne by simple up and down movements in the air. SmartBird was to be different. The developers set to work with great enthusiasm. The researchers came up with a brilliant idea. They set out to develop SmartBird as a biomechatronic overall design. This means that a bionic lightweight mechanism is combined with electric propulsion technology, smart control and regulation systems, and intelligent software for the control, monitoring and optimization of the flapping wing movement in real time. Fluid dynamics theory was also incorporated, and the project was carried out under scientific supervision. Tests and measurements were carried out, and various wing contours developed and discarded. Tests and measurements were carried out, and various wing contours developed and discarded. A great many tests were needed to finally arrive at the appropriate shape of the wings and their optimum angle of inclination. The outcome of this cooperation was a wing which had not previously existed and which many researchers had not thought possible. The new wing combines two functions of bird flight: propulsion and lift. The next challenge was to enable SmartBird to modify its wing position during flight in order to adapt to changing airflow conditions. The outcome was a sophisticated control software that left nothing to be desired. By means of two-way radio communication, the condition monitoring software allows various parameters to be monitored, such as wing position or torsion. If you look at the wingtip right now, you'll see the twist. I'll adjust it up and down. We can determine the motor's position by means of Hall sensors. And we can analyze the position of the wing's surface with high precision using a microcontroller. We can optimally adjust the torsion as a function of the wing's position and the speed of their beating motion. By this means, we attain optimal efficiency for SmartBird. With condition monitoring, the team remains constantly informed of operating data such as battery charge level, power consumption, and input from the pilot. The first test flights are about to take place. Tension mounts for the members of the team, and their expectations are high. After all, countless hours of work have been put into this one model. SmartBird must now prove that it can fly. The first test flights are launched by hand, but SmartBird refuses to remain airborne. The tests repeatedly fail. The bird can't fly more than a few meters. The team is disappointed, even though this is just the first prototype. They had expected too much. After all, it didn't have to succeed at the first attempt. But questions are asked and answers sought. Why did the test flight fail? The entire construction, inspired by the natural model, is now about to be revised. SmartBird is to be made lighter and therefore more energy efficient. At the same time, the bird's center of gravity is displaced to make its flight more stable. A sketch provides the basis for the technical drawing. This is then transferred to a computer. The computer then generates the data for the automatic milling machine that cuts the individual parts out of a thin sheet of carbon fiber. SmartBird is made up of a total of about 130 components such as these, which ultimately constitute the bird's mechanical structure. Special attention was given to ensuring a lightweight design for the flapping wings in order to keep the mass of SmartBird's moving parts to a minimum. Carbon fiber and lightweight foam plastic were the obvious materials for this application. Here, for example, we have a wing rib made from carbon fiber, which was milled in a network pattern from a very light structure and weighs about a gram. And for this torso structure, we of course made the skeleton from lightweight foam plastic. When assembled, the torso weighs about 26 grams. Once the parts are assembled, the future contours of SmartBird become visible. The construction is now complete, and all issues seem to have been clarified. The wing unit consists of a primary or hand wing for propulsion and a secondary or arm wing for lift. An electric motor provides the wing's flapping movement via a two-stage gear. Both the flapping and bending forces are conveyed from the transmission to the hand wing via a flexible link. The crank mechanism has no dead center and thus runs evenly with minimal peak loads. This ensures smooth flight. At the end of the hand wing is the servo motor that actively rotates the wing. 3 sensors make it possible to determine the exact position of the wings at all times. The opposing movement of the head and torso sections in all spatial directions is synchronized by means of 2 electric motors and cables. The torso thus bends aerodynamically with simultaneous weight displacement. This makes SmartBird highly agile and maneuverable. Final testing at Festo's Technology Center. The performance data are excellent, and the forces deployed by SmartBird impressive. This is the moment of truth. All the new findings have been implemented, and there's nothing more standing in the way of a new flight test. The development team is nervous. All the effort over the past months is now being put to the test. It's now time for the test flight that will show whether the inventors have taken the right course. The takeoff is successful, but the team is completely unprepared for what happens next. It's difficult to maintain SmartBird airborne. It crashes time and again. The team has a quick discussion, but the tests fail once more. There's an air of resignation and despair. Have all their efforts come to naught? Just what have they done wrong? The fact that the bird can't be properly controlled gives the clue. Improvisation is now called for. A rudder is hastily cut from a piece of foam plastic and attached to the rear.
So, okay.
SmartBird can then really show its capabilities. SmartBird gradually gains height. This is the moment the team has been waiting for. The bird flies and looks very similar to its natural role model. SmartBird can now be reliably and precisely controlled. Its wings, torso and control unit interact successfully. SmartBird can take off, fly and land under its own power. And now for the final challenge. What worked so well indoors must now prove convincing out in the open. Never before has SmartBird taken off or flown outdoors. Confidently it takes off, flies through the air and reaches an impressive height. The control unit works just as it should. The team is enthusiastic, and SmartBird fulfilled all expectations. In my estimation, SmartBird is far more efficient and reliable than anything else ever built in this field. The decisive factor is the active torsion. This makes for such a high level of aerodynamic efficiency as to give our bird much more thrust for the amount of primary power that's available. Propulsion and lift are generated solely by the flapping of the wings and require only 23 watts of power, and this with a total weight of only 485 grams and a wingspan of 2 meters. SmartBird attains an aerodynamic efficiency factor of up to 80%. It's thus an excellent example of functional integration, resource-efficient extreme lightweight construction, and the optimum use of airflow phenomena. SmartBird flies almost effortlessly through the air. The scientists and engineers at Festo have succeeded in further stretching the limits of feasibility in flight. On the Baltic coast, SmartBird is given its first opportunity to fly together with other gulls. This is a very special moment for Marcus Fischer, who provides us with a summary. It makes me very happy to see our bird flying here together with the real gulls. This is a fantastic experience. The SmartBird project has taught us at Festo a great deal about energy efficiency, particularly in the matter of airflow optimization. Only when the wings are twisted to just the right position can we exploit the airflow to the full, so that the bird can fly with active torsion. Another issue is control and regulation. Only when the flapping action and the rotation, in other words, the active torsion, are in perfect harmony, can SmartBird at all succeed in taking off. We'd never thought we could get as far as this. The scientists and technicians from Festo have achieved what few had thought possible. They have succeeded in decoding bird flight.